Okay, I'm going to start 5.2, which is all about the derivative of exponential functions. But before I do, I want to revisit this question, which is surprisingly easier than I thought. First, they want you to they tell you the cos x of the and the sine x of a hyperbolic function. So this is true. And then they ask you to prove the derivative of the sine x will simply equal the cosine x, which is actually very easy to show. The derivative of this is simply a half multiplied. What's the derivative of e to the x? It's e to the x. What's the derivative of this? It's the same function times the derivative of that, which is minus 1, which becomes plus e to the x. And we quickly see that that's cos x, so that's true. The derivative of sine x is equal to cos x for the hyperbolic function. If we take the derivative of this one now, that minus now comes down and changes it back. So that means the derivative of cosine x, that means the derivative, this is cosine for hyperbolic x, is this, the derivative of that is the sine hyperbolic x. So we've definitely proved these first two. In the second one, you have to prove the derivative of tan x, assuming tan hyperbolic x is equal to sine hyperbolic x over cosine hyperbolic x. So they're assuming this is true, which means you take the quotient rule. Quotient rule says I take that and square it, which they've done here. Right? So I know that I don't really have to touch that because they haven't touched it. I take the bottom function, which is cos x squared, which is cos x hyperbolic rather, and I multiply it by the derivative of cos x, which I've discovered is sine x. So all I do is I multiply it by the same formula as sine x. Then I have to do a subtraction. Clearly that's oh, sorry, I don't take the sine x. I have to multiply the bottom by the derivative of the top. And the derivative of the top is simply cos x squared again. Simply cos x squared again. Then I have to subtract the numerator function, which is simply sine x, times the derivative of cos x squared, which I discover is also sine x. Like that. Well, it's not that bad. So notice it's a half times a half times a half times a half. So the half is going to be in there no matter what. So I can take a half out entirely. So I'm going to take a half out entirely. So that I'm left with this times this minus that times that. Actually, it's not a half that's coming out, it's a quarter. Because the half here is a quarter. So that whole thing is going to become a quarter, and the front of this one is also going to become a quarter. So I'm going to take actually a quarter out. Okay? I'm actually going to take a quarter out. And that allows me to get rid of all those little halves. If I multiply this here, I get e to the x squared. If I multiply this, I get 1 plus 1 e to the x times e to the minus x. And again, it happens here, so I have two of them. If I multiply this, I get plus e to the negative x squared. Well, keep in mind this minus is going to apply to everything in this bracket, but I get very similar things here. I get e to the x squared minus 2 e to the x e to the minus x plus e to the minus x squared. Now I could actually resolve this this part right here quite easily, but I'm not going to. This minus applies to this, so these cancel out. This minus turns just to plus, so these two add together. So I get a 4 e to the x e to the minus x, all multiplying. This minus turns this into a minus, so this e to the minus x squared minus e to the minus x squared cancel out. And that's all I'm left with, a quarter times 4 times e to the x times e to the x minus 1. Well, a quarter times 4 is that. And when we have exponents to the same base, you can add their exponents. Well, x plus minus x is x minus x, which is 0. So you get e to the 0, which is 1. And therefore you've proven this is true. The only other thing I would note in the textbook is take a quick look at 18 here, where e has another definition. And it's not super important, but it's interesting to note. So we're going to go on to the derivative of 2 to the x, 3 to the x. And it's interesting to note that they don't really have a very good explanation or proof. And I gave a proof before, which isn't too bad. So go look at that, or go look online. But they start to do it by the standard method, minus 2 to the x all over h. And they put x plus h minus 2 to the x, which is the standard rule for a derivative, all as h approaches 0. Well, this allows you, the rule of exponents says when I'm adding exponents, that's the same as writing it as 2 to the x times 2 to the h, because that's when you can add their exponents, minus 2 to the x. Over h, all as h approaches 0. Well, this multiplier and this, they both have 2 to the x in common. So I can take 2 to the x out, and I'm left with 2h minus 1 all over h as h approaches 0. Well, 2 to the x doesn't have an h in it, so it's just a multiplier, which means I can just take this and put it in front of my limit. It's no longer an issue because it doesn't have an h in it. It's just a multiplier. And all I have to do is figure out this. Well, when I plug this in, I get a number like 0.69. And then you go on, and that doesn't really tell you anything. You can graph it, and you'll see it'll give this as an answer. And then you can go on and do it for 3 to the x, and you get a very similar thing. And you can take 3 to the x out, and you're left with the limit of h approaches 0 of 3h minus 1 to the h, and you discover this is another number. It's 1.1 something. And then you do it for 4, and you've got the same thing, and you discover another number, 1.3 or something. You also know that when it's e, it ends up being e to the x in front times e minus h to the 1 minus e to the power of h minus 1 over h, which you discovered was 1. So that we know that the derivative of e to the x is e to the x times 1. And through investigation, they just learned, hey, isn't ln of e 1? Maybe we're taking the original function and multiplying by the ln of e. So they took the ln of 2, and they discovered, yeah, that's the ln of 2. Then they took the ln of 3, and they discovered, yeah, that's ln of 3. Then they took the ln of 4. What is ln? Ln is the log base of e of anything. That's what a ln is. It's just a log base of e. So it's called the natural log. So they discovered the formula for an exponent was 2 to the x. The derivative of this was simply 2 to the x again times ln of the base number. Then they discovered that when, let's say it was 2 to the x squared plus 3x, they discovered the derivative was simply ln of the base times the actual function, times the derivative of the information up here. So whatever that is, they found out that that is the rule. Now, they don't show good proof of this, and I urge you to do more research on it. It's tough to prove. You can go backwards as I did in mine, but for now we're just going to assume those rules are true. And they summarize, they explain how they got there, they explain how they guessed at ln, and they also gave some examples of how to figure things out. They gave the summary, and they even showed that when there's a exponent in there, you've got to take the derivative of the exponent as well. And then they showed you that as bh minus 1 over h is equal to ln b. So that's something you probably should memorize. It's kind of a useful proof. I think there's a good proof online of this. And let's just get right into the questions based on those truths. Okay, they just ask you to differentiate using the tools you just learned. So it's essentially going to be the function itself times the ln of the base times the derivative of the exponent based on x. And there you go. So looking at that formula, we can see the derivative of this is going to be the function itself times the ln of the base, ln of 2, times, what's the derivative of 3x? It's 3. So rewriting it, I like to write 3 times ln 2 because those are numbers and it's good to have the numbers in front, times whatever was the original function, like that. That's me. I notice the book likes to put the ln of 2 at the end. To me, a ln is just a number, though. Just like e is just a number, the ln of 2 base e is just a number. That's why I like to put it all up front. Do whatever your professor wants to see, but a right answer is a right answer. Okay, what about this one? Well, this is just two functions added. So you take the derivative of this and the derivative of that. The derivative of that is just 3x squared. The derivative of this is the same as the function times the ln of the base times the ln of the derivative of the exponent, which is just 1. So that's just that. I would put the ln up front. So you can see it's 3.1 to the x times ln 3.1 plus 3x squared is equal to the derivative of that function. What about this one? Well, even when they use t, it's still just the same rules. So I'm going to take that exact function. The derivative is times ln of 10, which is the base, times, in brackets, the derivative of this. Well, that's just 0, and that's just 3. So 3. And I would put the 3 up front, or way up here. So I would have 3 ln of 10, and then I would write the original function. Okay, what about these? Same rules, just you have to use more and more rules in combination. So I'm going to take this as a separate thing. We've got to find the derivative of it. We have to also multiply by the function itself and the ln of the base. So ln of 10. The derivative of this, they've got it in the wrong order, but it's essentially minus 6 plus 2n. I'm going to rearrange it, just as if you rearrange this. It would come out to 2n minus 6, because I like to always put the biggest powers first. So 2n minus 6 is also a multiplier. So you can put that up front if you want. That's all there is to that. What about this one? Same thing. We're going to eventually find the derivative of this, so let's put that over there. We're also going to multiply by the function itself, and we're going to multiply by ln 3. The derivative of this here is 2x. So in the front, we're also going to write 2x. So what we end up with is this. It helps sometimes to put brackets around the 3 to make sure, and brackets around each thing. Desmos especially likes to see brackets around the 3. That's where it was screwing up before. So all these are multipliers, and that's the derivative of that. What about this one? Well, the 400 is just a constant. So we know it's going to be just that as one of the rules. We also know we're going to take ln of the base. The base here is 2, not 400. It's going to be ln of 2. And we also know we're going to multiply the derivative of the exponent, but the derivative of exponent is just 1. So that's all we got for that. So if you want, it could be 400 times the ln here. But you just leave the ln like that because the ln is precise. You If your teacher asks for decimal places, then you have to punch in ln of 2 in your calculator, which we know is 0.69 something, something, something. The reason ln is more accurate is because there's no rounding errors. So that's number 1. Number 2. Much the same, except you're going to have to start using quotient rules and things like that. Okay, so this one, this x implies they're multiplying, so it's kind of badly written. But the quotient rule says I take this and multiply it by the derivative of that. The derivative of that is ln 5, and then just the function itself. And then I must add it, that's the product rule, to this as a function alone times the derivative of this, which is 5x to the 4. Now personally, because it has a 5 to the x in it, and it has an x to the 5 and an x to the 4 here, I'm going to take out, I'm going to factor out this 5x to the 4, and I'm also going to factor out an x to the 4, because that's the most I can take out of them. And I'm left with x times ln of 5 plus 5, all in brackets like that. And essentially I'm saying this is going to be multiplying through to there. And sure enough, if you look, oh, I took the 5 out, so it's just 1. No, I just took the x to the 4 out. So you're going to, if I was to multiply through, you could see that I would return to what I have up here. But I find this is cleaner, especially if I just want to do one calculation over here. I don't want to have to do it once here and then once here. It also lets me only, that way I also do x to the whatever only once. And there's one x in there. So there you go. What about this one? Well, the base here is 3. So it's the same product rule. I take this and I multiply it by the derivative of this, which is ln 3, times the actual thing itself, times the derivative of the exponent. Now I've got a few things in common, 2x and 2 and x here. So I can put the 2x squared here when they multiply. That's what happens. So that's the first part. Then I must add just this function times the derivative of that function, which is just 1. I can see that I have this in common in both, so I'm going to factor that out. And that's all I have in common, which means this is going to disappear into a 1, and this is going to become a 1. And I put a bracket around it. So I'm left with 3 to the x squared times 2x squared times ln of 3 plus 1. If I was going to distribute it, I'd do that. Just makes the calculations a little bit easier if they're asking me to calculate afterwards. What about this one? Well, you could use the quotient rule, but I prefer to notice that this is the same as this, which means I'm going to take the first function and multiply it by the derivative of the second function, which is just minus 1 t to the minus 2, and I'm going to add the derivative of this function, which is ln 2 times the function itself times the derivative of the exponent, which is just 1, times this function. And I'm immediately going to notice that I have a 2t in common, and I have 1t to the minus 1 in common. So if I put the t's back down at the bottom, let's do it that way. If I put the t's back down at the bottom, This becomes t squared here. And this becomes over t over here. Now I have a choice. I can either put them on the same common denominator and add the numerators, or I could factor something out of both. I can see that I have 2 to the t out of this one. Oh, no, I can't. Yeah, it's times minus 1, so it's minus 2 to the t. And this is a plus here. So I can take 2 to the t out of this one, and I get 1. And I can take 2 to the t out of this one, and I'm left with ln t over t. So that would be a simplified version of it if I wanted to. I could also take 1t out of them, and I'd be left with this 1 over t here, and this like that, if I wanted to. Various ways you can represent it. This one too, I'm going to do, but I'm going to do this one on the quotient rule. Quotient rule says I take this, and I square it, so it's going to be to the 4 now. And I put this function times the derivative of this function. Well, what's the derivative of this function? That square root is the same as 2/2. So the derivative of this function says I have to, and now I can distribute that through. I can just multiply that times the x, and that x becomes a 1/2x. That's the rule of exponents. If I take the derivative of that, I have to take ln of 3 times the exponent itself times the derivative of that, 1/2. And I have to subtract in brackets, always use your brackets, the derivative of this numerator, which is 2x, times this function, like that. If I make the minus, just get rid of the brackets, it becomes minus that. Right away I can see there's a 1/2 in this, but there's not a 1/2 in that. So, I mean, I could pull out a 1/2 from up front, which I'd have to do if I want to put the 2 here. I can't just put the 2 down here because there's no 2 over there. But if I factor out a 1/2, and what else can I factor out? I can factor out 1x, and I can factor out 3 to the 1/2x, the actual function, like that. And this becomes x times ln of 3 minus, and that just becomes 2 because the x is factored out. Oh, actually that becomes 4 because when I factor out a 1/2, I divide it by a 1/2, which is the same as minus 4. So I'm just going to try to correct that. 4, 4, 4. That's not very good. 4, 4. And that x is gone, and that's gone. So I'd just be left with that. And now that I factor out the 2, I can put the 2 down here. That's the only way you can put the 2 down there. So that's one way to do it. I can also notice that I have an x to the 4 here and an x up here. So I can get rid of this x, and that just reduces this x to the 4 to x to the 3. And that's about it. Now, the answers will vary on this one because there's so many ways you can write it. But to me, that's the cleanest written version of it. Then they're going to get into specific problems. Here's 3, 4, and 5 I'll do. Like that. If this is a function, that times that, that's what that x is, determines values where the derivative will be equal to 0. In other words, determine where it has maxes and mins. Let's take that to another page. First, we need to take the derivative, and we need to get rid of this x so it's not confusing. So the product rule says I'm going to take the derivative of the first one, which is ln 10, times the derivative itself, times the derivative of the exponent, 3, so I got 3 up here, times this function. And I'm going to add this function alone times the derivative of this function, which is ln e. What's ln e? 1, so we don't have to write it, times the derivative itself times the derivative of the exponent, which is 4t. And now I've got to set it to 0. But before I get it to 0, let me simplify it a little bit. Notice that I've got this in both of them and this in both of them. So if I factor that out, I'm left with 3 times ln of 10 plus 4t, because this could multiply through both of them. Now if I set it to 0, it's a lot easier, because I simply divide both sides by this, because this is a multiplier into that. I can divide both sides by it. It's clear it disappears here and disappears here, and that's why it's easier to figure those out. If I solve for this, I go 4t is equal to negative 3 ln 10, and then I can divide by 4. And I can even leave it like that, or I can find an exact number. It depends what the book wants, but you would take ln of 10, which is just a number, you multiply it by negative 3 and divide it by 4, and you get this number, which this should be a peak. This is the value of x is equal to that, will be a peak or valley of it. Now if I were to put it back in there, and I were to take it and just put it as a memory, and I multiply it by 3, or better yet, I take 10 and put it to the exponent of open brackets, 3 times that minus 5, close brackets, equals, I get that. Get this weird number here. So that's one of the y values. And then if I take the other one, and I take e, and I put it to the power, open brackets, of 2 times that squared, close brackets, equals, ooh, I get a huge number. Let's make sure that. What is this squared? That times 2 is that. Let's replace our memory with that. And let's put e to the power of that. Yep, I get this huge number. When I take the first number and subtract this, in other words, I'll just make this negative, and I'll just add the other number. Oh, let's go back to that. Yeah, I've got to clear it again. E to the power of that. Yeah, I get this huge number. Let's clear the memory and put it in there. When I subtract 6.59, this from 6.59, which is the same as making this negative and adding 6.59452. I get this, which is the y value when this is the x value. The y is equal to that. So right there, I'm going to find the point on this graph where this is either a maximum or a minimum. Let's see if that was true. We're going to pull up the calculator here. We're going to put 10 to the power of 3t, what was it? See if we can see it. 3t minus 5. And we're going to multiply it. 3t minus 5 up here. Let's put it in brackets. 3t minus 5. And then we're going to multiply it by e to the 2t squared. And it doesn't recognize. Let's do f of t is equal to that. There we go. And then we're going to find the negative. We're going to find f of t is equal to 0. And it's telling me there's not a 0. Pretty sure there is, though, because that's going to be a min. Interesting. Let's try new equation there. When is f of t is equal to 0? Let's just change this to x because for some reason it's getting confused. There we go. There. Yeah, it's telling me right there. And sure enough, that's the numbers I found. This is indeed a minimum. Let's see if it's minus 382. So let's find, first of all, let's see when that's, it's saying it's minus 1.727. So let's find f of minus 1.727. Oh, no, it's saying it's minuscule. So I did some sort of calculation error when I did it up here. Oh, I know what I did. I wasn't supposed to subtract them. I was supposed to multiply them. But I did some sort of error in this one. That's okay. We did indeed get the x value. Yeah. For some reason I was subtracting them. Yeah, this would be 10 to a negative number multiplied by that. Okay, yeah, it'll be a very negative number. There you go. At least we got the right answer for t. T is indeed 1.72. If we go to the book, it'll show us that. Notice it keeps it in long format, though. It keeps it like this. Minus 3 times 10. They kept it in this format. On to the next question. I just want to get rid of one of these here. There we go. Okay, what about these? Determine the formula of the tangent. Okay, so they want the formula, the equation of the tangent. And they're going to do it twice. They're going to do it twice. First, we got to find the slope when x is 3. So we need to take the derivative. And the derivative of this is just 3. It's just the function itself times ln of 2 times the derivative of the exponent, which is just 1. And we need to find that when x is 3. So when it's 2 to the x, which is 8, times 3, it's 24 ln 2. And we're going to find that out. 24 times ln 2. And we get this. So that is the slope. when x is 3. But we should punch in x is 3 here to figure out what y is. Well, it's clear that it was 24. So 2 to the x times 3, 24. Y is 24. Well, we can't figure out the slope of the tangent because the slope of the tangent is a line. And we don't know b, but we do know y, and we do know x, and we do know m. So we know all of those three things, which means that 24 is equal to 16.635532 times x, which is 3, plus b, which, rearranging, b is going to be equal to 24 minus that. So we just need to do that. So we're going to take 24 minus 3 times, open brackets, 24 times the ln of 2, close brackets, equals minus 25.91. B is equal to minus 25.91, which means the entire equation for the line is y is equal to 16.64, let's say, x minus 25.91. And if we go to our answers, we discover it right there is correct. Oh, they like to do one weird thing in the book. They like to put it in standard formula, which means we got to get it all to one side. So it's clear this minus, when I get this to that side, it's going to become minus 16.64x, and this minus 25.92, I guess, is going to become plus 25.02, plus y is equal to 0. So they like to put it in the standard line format, whereas I like the slope line format. It's the same equation. Doesn't matter how you rearrange it. Okay, let's do this one. It's the same thing, except this time they give us the y. And the derivative of this is simply ln 10 times the function itself, and the derivative of that is just 1. So we need to know when that's going to be equal to 0. No, we just need to set the x is equal to 1 here. So it's just ln 10 times 10, and we get this. .03. So that means we have the equation now, and we need to put it into line format. And when y is 10 is equal to 23.03 times x, which is 1, plus b, which means that b is negative 13.03. So now we can write it. Let's write it in the standard line format. First, we can write it in in this format. And when I rearrange that, I get minus 23.03x plus y plus 13.03 is equal to 0. Let's see if we got that. Yes, we did. Good. Onwards. This is a little bit better. 16. I much prefer questions that relate to real things. So what's a half-life? When a radiation decays, it often decays in a half-life. So if I have 1,000 grams of plutonium, and I know it takes 74 years to go to half the radioactivity, I know that after 74 years, I'll have 500 grams. That's what a half-life is. I'm told that the time it takes to half the substance. This case, they give us a percentage. P of the material left after T years is given by this. So 100% of the material will be at time 0, which is equal to that. Okay? So To determine the half-life, I need to know the initial amount of the substance. The initial amount of the substance is when t is 0. When t is 0 here, 1.1 to the 0 becomes 1.2 to the 0 becomes 1. And 1 times that is 100, which means there's 100 grams or whatever it is of radioactive material at time 0. I need to figure out when the percentage is going to be half of that, 50 grams or 50%. So now I have to need to set 50, which is half of 100, which is the half-life. When is that going to be equal to this? Well, first we're going to divide both sides by 100. And I get 0.5 here. This disappears. 0.5. Now, the only way to bring minus t down is to take the log of both sides, or the ln, doesn't matter what. And that way, when I do take the log, the rule of logs allows me to take the exponent and bring it up front as a multiplier. If I want to get negative t times this all alone, I have to divide by the log of 1.2. So that means negative t is going to be log of 0.5 divided by log of 1.2. One other thing I have to do is divide by minus 1. So that means positive t is going to be minus 1 times whatever this is. Okay, that means I need to take log of 0.5 and divide it by log of 0.2 and click equals and change the sign. 3.810 years. So it's going to take this long in years to go from 100 grams or whatever it is to 50 grams, or 100%, since it's in percent, 100% to 50%. So that's my first answer. I think they're probably just going to round up to 2 years. How fast is it decaying at when x, or t rather, is 3.807? So for that, I need to take the derivative of this and find out, when I punch in this value of t, what the decay rate is. So to take the derivative of that, I know I just take the function, then times ln of 1.2, not log, ln, times the derivative of that, so it's going to be minus 100. If I set this to minus 3.81, I have to find out 1.2 to the negative 3.80. So I have to find out 1.2 to the power of 3.80 negative. I get that, which makes sense. It's essentially a third. Let me just see something here. Yeah, okay, that makes sense. So 1.2 to the power of 3.80 negative is 0.5, and then when I 0.5, yeah, then when I multiply that by negative 100, I get that, and then I have to multiply that by the ln of 2. So I get this, and I hope that's right, that it is decaying that much percentage per year at year 3.8. I'm going to check my math again. And I'm going to put 1.2 to the power of 3.8. Oh, and then I'm going to take the reciprocal of that. Yeah. I'm going to multiply that by ln 2. I'm going to multiply that by negative 100. I got the same answer. So my statement still stands. It's decaying at that rate. So let's see if we got it. No, we didn't. We got the years it takes to, we got the correct year, but we didn't get the correct percentage. How fast? How fast? Let's try the derivative of this again. The derivative of that is going to be that times the ln of 1.2 times -1. And that's when I have -3.8 years. Maybe they just want the percentage at that point. So 1.2 to the power of 3.8 negative times 100 no times, oh, was I taking ln of 2? I was taking the ln of 2. My bad. It is indeed -9.12. I think I got it. Yeah. I accidentally multiplied by the ln of 2. So that's what happens when you don't write down correctly. Number 7. This one's very confusingly written. They're saying that Canada was putting out payments that were interest, dividend payments from 1967 to 1979, where year 0 is 67. Year 0 is 67. That means if year 0 is 1967, then year 12 is 1979. And they want to know where T is the measure in years and P is the total payment. Determine and compare the rates of increase for the year 1968, so 0, and 1978. So the rates of increase would be the derivative of this at year 0 versus the derivative of that at year 12. Interesting, if that's what they mean by the ratio. Also note that when year 0 happens here, this whole thing is 1. So the initial payments are 5 with 8 zeros. $500 million. Since this will only go up, those are only going to go up. So the rate here should be much steeper than the rate here. Let's find the rate of change. So you're going to take the initial exponent, which is that. You're going to multiply it by the ln of e, which we can just ignore because the ln of e is 1. And then we're going to multiply it by the derivative of the exponent, which is just that. So that's the rate of change. At year 0, it's going to be this times the 0.02. So it's going to be 5 times 10 to the exponent of 8 times 0.20015. So that's the rate of change in the first year. It's going up 100 million essentially. Rate of change year 0 is per year. Rate of change when t is 12 is a little different. We have to take this item here and multiply by this and put it in the power. I'm going to do this in multiple steps. I'm going to take, don't know why I opened that, I'm going to take 12 and I'm going to multiply it by 0.0, see? I'm going to take 12 and multiply it by 0.20015, And I'm going to store it in memory. Good. Then I'm going to take e, and I'm going to put it to the exponent of that memory. I'm going to try that again. I'm going to take e, and I'm going to put it to the exponent of that memory. And I'm going to clear memory, and I'm going to put that in storage. Then I'm going to multiply that by 0.20015. And I'm going to multiply that by that. And I'm going to get this, 1.1 billion. Rate of change, and I'm going to check that twice, is per year. And then if you look at the two, you have to take a ratio of them. So you have to take this, that's why this question is confusing, and divide it by the first one. And you get the rate of change is 11 times faster. That's assuming, 11.04 times faster. That's assuming I did the calculations right here. So I'm going to check my calculations twice. And this time I'm going to do it e to the exponent of brackets 0.20015 times 12, close brackets, equals. Then I'm going to multiply it by, open brackets, 5 times 10 to the exponent of 8 equals. Then I'm going to multiply that by 0.20015. Yeah, I get the same thing I did before. So I'm going to assume that that's my answer for part A. Assuming this trend continues, compare the rate of increase for 1988 with the rate of increase for 1998. So 10 years apart. And this one is year 20 compared to year 0. And this one is year 30. So you got to do it all over again. Jesus. Okay, let's try it all in one go. We're going to take e. I'm going to take the 30 first. We're going to take e to the exponent of 0.20015. We're going to try that again. We're going to take e to the exponent, open brackets, of 0.20015 times 30, close brackets. We're going to hit equals. We're going to multiply that by 5 times 10 to the 8 times 0.20015. So this is how much they're spending in year 30, $40 billion. And we're going to put that in memory. And actually, we're going to write it down. Year 30, spending that per year. Now we've already put it in memory, so we're going to clear. And we're going to do e to the power, open brackets, 0.20015 times 20, close brackets, equals, times 5 times 10 to the power of 8 times 0.20015. And we're going to hit equals. And I'm going to just copy that down first, because that's year 20. And we can just ignore the last little bits. And I'm going to divide the two, and you might say, well, you're dividing it in the wrong way, except that I'm going to flip them. And I get 7.4 times faster. So the rate has increased. Rate between 68 and 78 was 7.4 faster. which might not make sense right away until you realize that the first gap was 20 or 12 years apart. This gap is only 20. Well, hopefully I'm right. What's the last question? Let's not bother with that last part. Let's just see if we got the right answers. It's really weird because they give they're giving the actual, we got the second part right, 7.4, but they didn't actually calculate the first part, and we didn't quite get the right amounts. Oh, I can see why we didn't get the right amounts. It's 1968, not 1967. So for this first rate of change, I had to use a 1, not a 0. Okay. If I do the 1 e to the 1, e to the exponent of open brackets 0.20015 close brackets, I get this. That's different. Yeah, times 5 times 10 to the exponent of 8 times 0.20015. Yeah. Do I get what they got, though? You're saying it's, yeah, there we go. There's that 122 right there. Yeah. So yeah, I got what they got. I just took the wrong one. So, knowing that it's 122, now they still say that it was this in year 78. Oh, another mistake. I was using 12. I was assuming they were going from this. They're using year 11, not year 12. So anyway, the methods I've shown is correct. I should have read the years here. I assume they were using the same years stupidly, but they went 1 year up and 1 year down, which is year 1 and year 11. Anyway, on this one, I did get it right. And probably the answer to this is yes. The method I just used is correct. I just took the wrong years. Frustrating. Determine the equation of the tangent of the curve at the point in the curve where x is equal to 0. Graph the curve and the tangent at this point. Okay. Well, I'm going to maybe let the computer graph it, but anyway. We'll go for it. So they want the equation for the tangent of the curve. It's hard to think what this is going to look like, except it's minus 2 to the whatever, 2 to the x, is a growth curve. The minus and square just means it's going to happen faster. Minus means it's going to reflect over here. So we're actually going to have a graph that is going down like that, quite steep. When x is 0, we can say that it's 2 to the 0, y is going to be 1, because it's always 0, 1. So it's going through the y-axis. So it's going to be starting to flatten out. Well, we can graph the curve just by what we've just figured out now. But let's go ahead and proceed. The derivative of that is ln 2 times that times negative 2, which is the derivative of the exponent. At y0, the dot is 1. And just to get some more points, at y1, x is equal to 1, it's 1/2. When x is equal to 2, it's 1/4. When x is equal to 3, it's 1/8, which means at -1, x is going to be this. Oh, it's going to sort of do this. -1 here becomes 2, -2. 2 to the -2 is 1/4 again. So -1, it's a -1/4. When this is 1, -1, it's 1 still. -1, it's 1/2. Because it's squaring, it's going down again. So -2 is 4 minus 4. One quarter. No, 2 to the 4 is 1/16. So it seems to be doing this weird bump here, because it's going up and then down, and 0, 1 appears to be the highest point. So here's the formula for it. We're going to set it equal to 0. First of all, for that to be 0, we're going to divide it all, and we're left with this. We cannot take a log of both sides, because there's no such thing as log of 0. Oh, I see. It's not when, my bad, it's not when x is at 0. So they're not saying find a peak. They're saying set for 0. So you get 2 to the 0, which is 1, times -2, which is -2, times ln of 2. So you got to take -2 and multiply it by the ln of 2. And you get negative 1.3862 or whatever. Which means the slope, or the rate of change, is equal to that. To do the formula, we know that when x is 0, y is 1. And you do y is equal to, you do 1 is equal to mx, but we know x is 0, plus b, which means b is 1. So that means y is equal to minus 1.386 x plus 1 is the formula. The question for me is, what does this graph look like? So I'm going to do a bunch of x and y values just to get an idea. And I'm going to start when x is 0, y is 1. When x is 1, we get 2 to the -1, which just means 1 over 2. When x is 2, we get 2 to the -4, which means 1/4. When it's 3, it's 1/8. When it's -1, though, we get the same thing. When it's -2, we get the same thing. When it's -3, we get the same thing. So again, it's weird to me. This should have been a peak, because it looks like it's going up and then down. Let's graph it. Okay. Well, to me that should have been a slope of 0. Yeah, it's saying it's a slope of 0. So why did the derivative come up with that? Maybe I did something wrong. So the derivative of this is minus 2 times the derivative of itself times ln of 2. When x is 0, this is 0, this is 1. So it should be minus 2 times the ln of 2. Yeah, it still comes up with a slope. Oh, stupid. Stupid, stupid. The derivative of that is not minus 2, it's minus 2x. So when x is 0, the whole thing comes out to 0. Stupid. Yeah, so it is a peak as I thought. Dumb. Sorry, just tired. All right. Don't know what the hell that's doing. No. Don't even know why that opened. Okay, the last one. So I kind of botched a lot of this. Been botching a lot of them lately. That's okay. The techniques are right. The results are usually just moving too fast. The velocity of a car is given by this, so it's velocity based on time. Graph the function, describe the acceleration of the car. So acceleration of the car is the derivative of velocity. If we look at this at time 0, the speed is going to be 1 minus 1, which is 0. Velocity is 0. If we look at time 1, the speed is going to be 120 times 0.15. Okay? The speed is going to be 120 times 0.15. 18. If we look at time 2, the speed, and you might say, why is the speed going up? Because this fraction is actually going down as time goes up. Because anything to the below 1 to the power is going to be a decay curve. So this 1 is going to get bigger and bigger and bigger until close to a max speed of 120. So we're going to look at just time 2. So it's 1 minus 0.85 to the exponent of 2 times 120. 33. Looks like it's close to doubling. 3. It's going to be clear. 1 minus 0.85 to the power of 3 times 120 is 46.3. So if I'm going to graph it, it looks like it's slowing down too. So if I'm going to graph it, it's going to go 0, 0, 118, but not quite a double. Like that. It's going to go like that. And it's going to do this, and it's never going to quite reach 120. And how do I know that? Because if I turn this into infinity, it becomes almost minus 0, but not quite. And 120 times a little less than 1 will always be below 120. So I'm going to have this thing like that. Let me figure out the acceleration of the car. Is the derivative of that. The derivative of this is 0. The derivative of this is minus 0.85 times the overall function itself, no, times the overall function of this part times itself, times the derivative of t, which is 1. Just to confirm that, if you want to make it simple on yourself, you can multiply the 120 times, the 120 here is going to be 120. It's going to make a derivative of 0. But 0.85 negative times 120 is going to be this, minus 102. That'll make my life a little easier. So that means the derivative is going to be minus 102 times the derivative itself, or times the function itself, I should say, times the derivative of that, and describe the acceleration of the car. Oh, I forgot the ln, sorry. It's going to be minus 102 times the ln of 0.85 times the function itself, which you can either write as, you can just write it like that if you want. And really that just becomes this. Oh no, it becomes that. And that becomes 120 minus 102 to the power of t. It's never going to reach 0. Describe the acceleration of the car. I think I did. It's accelerating slower and slower and slower, and it's reaching max speed of 120. This can just be seen because this is a flip in the x-axis, and this is a decay curve. So if I take a decay curve and flip it to the x-axis, that's what I get. Let's have a look at it. And we'll put it to the negative x. We'll skip that. Just to the x, not the negative x. There we go. Let's put it on a scale we can see it from 0 to 120. I'm going to put y is equal to 120. And if you zoom in, no matter what, it's never going to reach 120. There we go. You can even pull up, let's see what the other curve looks like. So the derivative curve is the rate of speed velocity is decreasing, which makes sense because his speed acceleration is decreasing, which makes sense because his speed is decreasing, right? So his acceleration is always going to be decreasing. It's always going to have a negative slope. Hard to see from the actual derivative, though. I think I could have simplified it a little bit. So the derivative is going to be that, which is the same as 120 minus 102 to the t. No. times 120 times 0.85 to the t times the ln of 0.85 times times 1. So I think if I took, so that's the actual thing, and then the derivative of that, I've got to take the derivative of the actual function. So that becomes this. Is equal to that. Let's see if I got that right. Yes, I did. We're going to call that g of x, and we're going to call that, there we go. Yeah. So this is indeed the formula, and you can see again that that's a decay curve multiplied by a number that's flipped in the y-axis. But this ln 0.85 might also create another flip, right? So you've got to figure out what ln 0.85 is. Yeah, it's negative 0.16. So if I multiply by that by negative 0.16, this becomes positive 19.2. And it's clear that we're dealing with a, got to get rid of this now. See how it compares to the actual f prime of x. Close enough. So that we can see that we're dealing with a decay curve still. And this is simply a decay curve that's flipped in the y-axis. So had I simplified it a bit more and find out what ln 0.85 is, I could have easily recognized the acceleration as a decay curve. Very complicated. Sorry so long. Sorry so many mistakes. But it's well worth investigating.